So as I've mentioned, this is a continuation of on hypothesis testing, but here we're going to be dealing with small samples. Whenever we are dealing with small samples, whenever we have small samples. Okay, so I want to start by recalling the central limit theorem. The central limit theorem has two parts, or we defined two parts of the central limit theorem. One, we said that if X has a normal distribution, if X has a normal distribution with mean equal to mu and standard deviation equal to sigma, we say that if X has a normal distribution with mean mu and standard deviation equal to that, then X bar, the statistic here, or the sampling distribution now of X bar, has a normal distribution with mean mu and a standard deviation, which is technically called the standard error, equal to that. So if X has a normal distribution, then a sample statistic, that is X bar, will also have a normal distribution with standard deviation, which is called standard error, equal to sigma over root n. And we said for whatever value of n, for whatever value of n. So here, it doesn't matter whether n is small or is large. All right, then that's part one. Then part two, we said that if X is not normal, if X is not normal, if X is not normal, or the distribution of X is unknown, it can be either way, or the distribution of X is unknown, then the distribution of X bar will also be normal, with mean equal to mu, just like the first scenario, and standard deviation equal to sigma over root n for large n. That's what we said. Then we went ahead and said that n is large if it is bigger than 30. This is what you're calling large sample. That's what you're calling a large sample. So I think that's the concept that we've been applying all through the hypothesis that we've been testing, okay? But now there comes a time when the first statement is true, up there is true. So we want to assume this, but when sigma is not known, so from one, if sigma is not known, there are two things. If sigma is not known and n is small, there are two things there. If sigma is not known and n is small, so when sigma is not known, it means that we're going to estimate it using the sample data. So when sigma is not known, we are supposed to get S. We are supposed to get S to estimate the value of sigma or standard deviation. But here there's a problem. If n is small, the sample estimate of sigma, that is S, is always biased. So there's a problem about the first statement if this guy is not known, because that means, because this is a population standard deviation, if the population standard deviation is not known and you have a small sample, then any estimate that you're going to get from the sample will be, the estimate of standard deviation from the sample will be biased, okay? And biasedness here means that it will always be smaller than the true value. It will always be smaller than the true value. Okay, so now to correct that bias, To correct that bias, we adjust the formula of standard deviation as follows. So we adjust the formula of obtaining standard deviation as follows. So I hope you remember standard deviation from a sample. Usually the formula is given by this. Summation of x minus x bar squared over n. So we're saying that formula will always give you a biased value of s if n is small, that is if n is less than 30. So to correct the bias, we multiply this formula here by this factor here, n over n minus 1. So that is what removes the bias. And as you can see, we can simplify this and it becomes summation of x minus x bar squared over n times n over n minus 1. You can cancel like that and you're left with summation of x minus x bar squared over n minus 1. So we adjust the formula to remove the bias. So we use that formula to obtain a standard deviation or the estimate of sigma. So in this scenario, we also switch from the normal distribution to another closely related distribution called the t distribution. When you have a small sample there, or when sigma is not known and you have a small sample, you also switch from normal distribution to another distribution called the t distribution. And we're saying that this t distribution is very closely related to the normal distribution. Okay, so the divisor in the above formula of standard deviation is called degrees of freedom. In the context of the t distribution. So usually we denote the degrees of freedom by d dot f, which is equal to n minus 1. This divisor, this value is the one that I'm talking about. We call it the degrees of freedom. Then let's look at how the shape of this distribution looks like. For a normal distribution, for a normal and t distribution with equal mean and standard deviation, the distribution looks as follows. So this is how it looks like. So the shape is the same. The shape is the same. They are symmetrical about the mean. So that's the normal distribution, which we all know. So we can put this as our line of symmetry. That's our line of symmetry. So this is a mean point. So if they have the same mean, a t distribution will look like this. So I'll use green here. A t distribution will look like that. So it is also symmetrical about the mean. and it continues all the way to plus infinity, minus infinity. So it's defined within the interval minus infinity plus infinity. Now, let me label it. So this is the t distribution. The red one is the normal distribution. So the shapes are almost the same. The only difference you will notice is that the t distribution has a sharper peak. So the peak is this point here, is a bit sharp compared to this one, which is a little bit flat. And as a sharper peak and higher, sometimes we use another word here, and higher or fatter tails, and fatter tails. So if you check the tails of the t distribution are a little bit higher than those ones of the normal distribution. These are the tails. As you can see, it is fatter than the red one. It is fatter than the red one. Okay, even on the other side. We see that the normal distribution dies out very quickly. Yeah? So this one remains up for some time, but in the long run, they coincide. They become the same distribution. So I want us to note that when n is large, the t distribution is approximately equal to the normal distribution. So when you pick a large sample, the second statement here becomes true. So you apply this statement here. When your sample size is large, you work with this statement here. You assume the normal distribution. You don't need to use the t distribution. You don't need to use the t distribution. Okay. Now, in order to find the critical values, of the t distribution, we need three things. Number one, we need to know level of significance. That is alpha. Alpha will always be given. And if it's not given, you just choose 5% most of the cases. So that is easy to see. The number two, you need to know whether it's a two-tail or one-tail test. You need to know that bit, whether you are performing a two-tail test or one-tail test. So those 2 points are similar, are common for both T and the Z distribution. The number three, you need to know the degrees of freedom. So degrees of freedom are not used in the context of normal distribution. Okay, so that is E of F, which is always given by n minus 1, where n is the size of the sample. So those are the 3 things you need to know for you to get the critical values of the T distribution. Okay. Now let's have an example. I'm going to get this example from your notes. So let's say I'm paraphrasing. A manufacturer claims that the mean content of the main ingredient of his products is 70%. You can think of a manufacturer of sanitizers, the hand sanitizers during this time of COVID. So you see there's a requirement by the Bureau of Standards to have the alcohol level, and alcohol here is the main ingredient, to have the alcohol level at 70%. So a certain manufacturer here claims that the mean content of the main ingredient of his products is 70%. Then we say you choose a random sample. You choose a random sample of 5 of his products and observe the following. So let me record the values there. We have 68, we have 62, we have 74, 67. So you've chosen a sample of, how many are those? Oh, there's one more, and 64. So you choose a random sample of 5 elements. So you see the assumption of randomness is always there. The sample must be chosen random. But as you can see now, we have not chosen a large sample. Okay, so these are the scenarios where we are saying, even if the distribution of all the products manufactured by this person are normally distributed, we may not want to use the Z distribution because a standard deviation from such a small sample or estimated from such a small sample will always be biased. But if we are told the population standard deviation, if you are told this is the value of the true standard deviation, you don't need to use the T distribution. You will continue using the normal distribution even when the sample is small. So we'll apply the central limit theorem. So this is the question: does this sample invalidate the manufacturer's claim? The manufacturer's claim. Does this sample invalidate the manufacturer's claim? So we want to test hypothesis here. We want to test the claim by this person here. Okay, so the steps of testing hypothesis will be similar to the ones that we observed in the context of the normal distribution. So the steps will be the same. So solution, let's see what we have here. We have 70. All these values are also in percentage. Yeah? So, but as explained in the question, this is a mean value. It's a mean value. So we are working with the mean. Just like the way I can say your mean score in a certain subject is 58% or 98%. So these are not proportions. So then let's not get confused. So we have 70 there, which is our mu naught. We have 70 there, which is our mu naught. So we need X bar from this data. So we need to calculate X bar for this data. And X bar for this data will be how much?
Seven.
6.7. Thank you. Yeah, so good. So we know that the number of observations is 6, it's 5. Huh? We also need to find an estimate of standard deviation. So let's do this together. We need to estimate standard deviation. So let's have the values here. We have 68, 62, 74, 67, and 64. So we need to find the standard deviation here, and we already have X bar is 67. As you know, Standard deviation is the square root of the sum of square of the arithmetic mean of square deviations. So here I need x minus x bar squared. I need that. So this will be 1. This will be how much? This will be, how much is this? This will be 49. Next, this will be 0. This will be 9. Okay, so I need to sum this value, summation of x bar squared. It gives us how much? 84, is it so?
84.
84. Thank you. So we need to get S, the standard deviation. And remember, because n is small, we shall adjust the formula of standard deviation and the divisor will be n minus 1. Okay. So this will be 84 divided by 5 minus 1, which is 4. What is the standard deviation in this case?
4 divided by 4.
4.58.
4.58.
Yeah, 4.58. Okay, so now let's test this hypothesis now. So this is the only bit that is different from what we've been observing in the context of the normal distribution. So this is the estimate of sigma now. Now let's define our null hypothesis. H naught is that mu is equal to mu naught. And our mu naught is how much? 70. We need to take H1, which will be mu. What are we testing here? What is the question?
Is the sum
Equals.
What is the nature of the alternative hypothesis to answer this question? Yes?
equal?
So there are 3 possibilities, either less than, or greater than, or not equal to.
Not equal to.
Not equal to.
Yeah, we're checking whether it is 70 or it's different from 70. So this is calling for a two-tailed test. A two-tailed test. And because alpha is not given, we use 5%. Alpha is 5%. Okay. So let's define or let's set up our critical region. So usually the curve for the t distribution will look like that one of the normal distribution. We don't need to put all the details to show that it is more peaked. Those details are not adding any value. But note this will be 0 here. That will be 0. So we need to have here and here two-tailed test to look like that. So here we need alpha over 2, which is 2.5%, which is again 2.5% or 0.025. So here we are going to have t critical, even here, t critical value. So the critical value of t is read from the tables. You read this value from the t distribution tables. I want to show you how the t tables look like. Huh? So the t tables are here. So we have the t tables here. The t tables, as you can see, the shape of the distribution is symmetrical. Is symmetrical, just like that of the normal distribution. So this is the central, this is the center or the mean line. So as shown in this diagram here, the t tables gives you the probability of, or the probability of it gives you the critical region being on one side, but you can always map it on the other side in case you want to do either a lower tail test or a two tail test. Okay, so in the first column here, we have the degrees of freedom. Yeah, so these are the degrees of freedom. And they are continuing. This table here stops at 20. Usually, most of them go up to around 30. Because we said that any sample which is larger than 30, then you consider that as a large sample and you use the normal distribution, not the t distribution. So that's why the table stops at around here, 20 or maybe 30. Most of the cases it will be around 30. Okay, so the first column is degrees of freedom. And as we said, degrees of freedom is always given by the sample size minus 1 when we're dealing with one sample. Okay, then the other column, the columns here, these ones are the different values of alpha. The different values of alpha that you can use. Okay, so the first one is an alpha of 40%, which is very unlikely. This is alpha of 40%. This is alpha of, we almost never use that. This is an alpha of 25%. We almost never use that. This alpha of 10%. We use that sometimes. This alpha of 5%. Okay, that is quite widely used. This is 2.5. You know, we also use that, especially when we're using two-tailed at 5%. This is 1%. And this is 0.5%, which is used alongside this when you're having a two-tailed test. And this one is a very small level of alpha, very small level of alpha. So these ones are widely used. From here up to here, those values are widely used. These ones are rare. These ones are never used. This one is rarely used. Okay, so for instance, in our case here, we have degrees of freedom. In this example, our degrees of freedom is 5 minus 1, which is 4. So if you want to find the critical value, and we are doing a two-tail test. So if we are doing a two-tail test, it means that this is the area that we shall be checking in our tables. We check for this area from our tables. We are not going to check 5%. We check this area because the tables are showing you this part. So we look for 0.025, 4 degrees of freedom. So 4 degrees of freedom is values in that row. So those are, sorry. So these are the values in the row of 4 degrees of freedom. Okay. Then we're talking about alpha is, the upper tail is 2.5%. So this is a value 2.5. This is a column. So the value, the critical value is here. 2.7. So this will be 2.77. So 2.77645, and you map it on the left hand side minus 2.77645. So that's how you get the critical values of a t distribution. If we were working with a one-tail distribution, one-tail test, sorry, at 5% level of significance, 4 degrees of freedom. It means that we'll work with this row, 4 degrees of freedom, but now the upper tail will be containing all the 5%. So you'll work with this one, 2.13 will be your critical statistic. If you're working with a 5%, one tail, let's say an upper tail, and you have 15 degrees of freedom, it means that you come to 15 degrees of freedom, 5%, you check this value, and so on and so forth. Okay? So that's basically the procedure. So let's go back to our question. So we have the critical value. So once we get the critical value, we have the critical region and the acceptance region. So the next thing is to obtain the T calculated. And the T calculated is obtained using the same formula we used for Z. If you recall, we were getting Z using this formula, X bar mu naught over standard error of X bar, like that. So we use exactly the same formula. We just come here and change the Z to T. So we use the same formula. So this will be X bar minus mu naught over standard error of X bar. Of course, we know where standard error of X bar is sigma. In this case, it will be S over root n. So S is the value that we obtained up there. So let's compute the T calculated for this problem. Our X bar is, so T calc, X bar is 67. Our mu naught is 70 divided by standard error of X bar. So standard error of X bar is, we got how much? 4.583 divided by root 5. Divided by root 5. So divide by square root of 5. You get the standard error is 0.4.
9.
Thank you. So, so that means our T calculated will be minus 3 divided by 2.049. Now we have minus 3.
Negative 1.4638.
46.
385.
Yeah, it's okay. Yeah.
Yeah.
So now, let's say where this value is falling. It is either in the acceptance region or in the rejection region. We go back to our diagram here, and we try to locate that value of minus 1 point or something. So that value will be here, minus 1.46. It will be somewhere there. It will be somewhere in the acceptance region. So we say that T calc, which is minus 1.464, falls in the acceptance region. So what do you do with the null hypothesis? Hence, we do what? What do you do with the null hypothesis in this case?
Reject.
We fail to reject.
To reject.
Yes.
Reject.
Hence, we fail to reject the null hypothesis at the 5% level of significance. We fail to reject the null hypothesis. So what is the conclusion in this case? The question was, does this sample invalidate the manufacturer's claim? Yes or no? What do you think?
No.
It does not. Yes. So this sample,
Yes.
yeah, you are saying yes.
No, it does not invalidate.
Yeah. So this sample does not invalidate the manufacturer's claim. So as far as the data we have is concerned, then there's no evidence to reject the manufacturer's claim. There's no evidence for us to reject the manufacturer's claim. Okay, so that is it. When you are testing hypothesis about one sample, you can do the same when you have two sample means. Two sample means with small sample, with when you have small samples. So nothing changes. So everything will look like what we did earlier, but when we're estimating the S, you need to use the formula that we mentioned here. When you're estimating S or the standard deviation, you will use that formula, this one. You'll use this formula in the two samples. You'll use that formula in the two samples. The other story will be similar to what we saw using Z distribution. Okay. So let me mention a few things there, especially the degrees of freedom. So let me start from H naught. H naught will be mu1 is equal to mu2. H1, mu1, either less than mu2 or mu1 is such that mu1 is greater than mu2, or H1 is such that mu1 is different from mu2. Okay. Then the t calculated will just be x bar 1 minus x bar 2 over standard error x bar 1, x bar 2. Okay. So the formula of standard error does not change. The degrees of freedom here will be n1 minus 1 plus n1 minus 2. Sorry, minus 1. You minus 1 everywhere. This is n1 minus 1 plus n2 minus 1. So it's the same as n1 plus n2 minus a 2. So that's how you obtain the degrees of freedom. You check the tables the same way we have done. You check the tables the same way we have done. So nothing changes. So we are not going to have an example on this because I think it should be easy for you to see. So that's a bit I wanted us to cover on a small testing hypothesis in the context of samples. So I want us to stop there as far as that bit is concerned. All right, so let's move on to what we call the correlation and regression analysis. And I want to point out that the kind of analysis that we assume that you've covered is in the domain of what we call univariate data. This is what we are assuming that you've covered before coming to this class. Univariate data. This is where you have just a single variable to analyze, okay? A variable like X only or Y only. So under univariate data, this is where you cover things like measures of, this is where you learn first graphical presentation of data. Graphical presentation of data using histograms, pie charts, and so on and so forth. Then here you also learn what you call the measures of central tendency. Hope you can remember the measures of central tendency. We have used them so many times in this class. Like we have the mean, the arithmetic mean, that is the median, the mode, and so on and so forth. We have measures of dispersion.
I cannot see the screen, Malim, you're sharing.
Oh.
I'm not able to see the screen.
Me too, I can't see.
You cannot see, yeah?
No, whatever you write.
The writing.
Yeah.
So you are writing, we can't see, but we can see the screen.
All right, let me know what you can see, yeah? Can you see the screen?
We can see correlation and regression, that's all.
Analysis only.
Oh.
Then the rest we can see.
All right.
Yeah.
All right, I think now you can see. I think I had touched somewhere.
Oh yeah, it is clear now.
Thanks for that. Huh? So I was saying that before coming to this class, we're assuming that you've done what we call the univariate data analysis, where you learn how to present data graphically using the various tools, and then how to obtain the measures of central tendency. That includes the mean, the median, the mode, and so on and so forth. You have also covered measures of dispersion. And the most important measure of dispersion is called the standard deviation, like the one we just computed up there. There are many others, like the mean deviation, the quartile deviation, the quartile deviation, the range itself, and so on and so forth. We're also assuming that you've been introduced to what we call skewness and kurtosis. Okay, so skewness is about the shape of the distribution. The lack of symmetry is actually what we call skewness. And as you've seen in this class, we were assuming a distribution which was not skewed, a symmetrical distribution. Then we also have what we call the kurtosis, which has something to do with the shape of the peak, whether it is flat or it is peaked. Like we have just seen that the T distribution has a sharper peak compared to the normal distribution. So kurtosis has something to do with that. Huh? So now we are going to introduce ourselves to now what we call bivariate data. Bivariate data, this is data comprising of two variables, and we shall extend it to multivariate data. So when we have data comprising of three variables, you find that the measures that you covered in statistics 1 or under univariate data analysis are not sufficient. They are not sufficient. So we supplement them with bivariate methods of data analysis or multivariate methods of data analysis. And some of the most widely used methods of bivariate and multivariate analysis are what we are calling correlation and regression analysis. We're going to start with correlation analysis. Correlation analysis. Now, when we talk about correlation, as you can see, we seem to be having core, and then we have the word relator. So it looks like we shall be talking about some relationships, and core signifies two. So basically correlation is for bivariate data. So under correlation analysis, we shall be looking or analyzing relationships between two variables only. So maybe I can give some definition here through paraphrasing. I can say that correlation analysis is a statistical analysis that measures, is a statistical analysis that measures and analyzes, the degree or strength and direction of relationships between two variables. So we analyze, we measure, and then we analyze the degree or the strength of relationship, and also the direction of relationship between two variables. So that's why it is core, because it's two variables. So there are two things here: the strength of the relationship and the direction of the relationship. Okay. So then we say that the measure of correlation is a number between -1 and +1. So I want to use a diagram here to illustrate that. So correlation is a number between -1 and +1. So this is 0. This is a straight line now. This is -1. This is +1. So from -1 towards 0, this is decreasing. That is decreasing negative correlation up to that point. And this one from +1 to 0, this is decreasing positive correlation. So the word positive here or negative is the one that tells us the direction. I'll explain that in a while. Then away from 0, from here all the way to +1, this is increasing a negative correlation. And the opposite here, from 0 towards 1, this is increasing positive correlation. If it happens that your measure of correlation is at this point, that is +1, this point here is called perfect positive correlation. If it happens that your measure is +1. If it happens that your measure is -1 here, then you say this is a perfect negative correlation. Then at this point here, 0, we say that there is no or there is 0 correlation. There is no or there is 0 correlation. Okay, so usually we can partition here. We can partition this. We can just use some rule of thumb and partition this into 3 parts like that. And you can say this is plus 0.3 plus 0.7. The same case here, minus 0.7 and 0.3. So any value which is here, you can say this is low. You can claim this is moderate. So this is low, negative. This is moderate, negative. You can claim whatever is here, you can say it is high, negative. Of course, those are very subjective statements, huh? Because somebody will want to say that minus 0.4 even is low, okay? Depends. So to avoid those kind of confusions, usually we test the hypothesis. To avoid the confusion of whether it is low, whether it is moderate, we check whether it is different from a given value in a significant way, okay? Or you check whether it is different from 0 in a significant way. So the same case here. So this is low positive. This is low positive. This is moderate positive. Moderate positive. And finally, what is here is a high positive. Okay, you can change the names to very high negative, moderately high, and so on and so forth. So you can change the description now, just the way you want. You can use your description to change the way you describe the values. Now the direction, when you talk about the direction, is given by the sign. By the sign. Huh? So when we talk about positive correlation, this is when two variables change in the same direction. When the two variables change in the same direction, you end up with what we call positive correlation. So that means either you have an increase, a positive and a positive, or a negative, a negative. So this is a first variable. Let's say y and x. Huh? This is y and x. So you find that when y increases, x increases. That will result to positive correlation. Or you can have when y decreases, then x also decreases. That is also positive correlation. And the converse is true. So we say negative correlation, and this happens when the two variables change in opposite or inverse, in opposite directions. That is either when one increases, the other one decreases, or when one decreases, the other one increases. So that results into what you're calling negative correlation. Okay, so this is maybe your variable x, this is your variable y, x and y. So when that happens, then you end up with what we call negative correlation. So diagrammatically, when we talk about positive correlation, will always be given by, if you are to fix a line or the trend line, it will always be given in that direction. That's positive. Huh? So you notice that as you increase, let me pick a point here, and I pick another point there. So if this is my X1, this is my Y1, I take this point, I increase X from X1 to this point, X2. So you notice that if I increase X from X1 to X2, then also the value of Y increases from Y1 to Y2. This is a positive leading to a positive. You can look at it from the other side. You can say, if I decrease X from X2 to X1, that's a decrease in X, that's a negative. Then so I'll be moving from here. My value of Y will be moving from here to here. So my value of Y will move from there to there. So that is negative. So we find that I have negative and a negative, or I have positive and a positive. That's what amounts to positive correlation. The negative correlation can be argued in the same way. So you have, that's the general trend. So if I pick a point here, if I pick a point there, and another point there, so this is my X1. So this X1 corresponds to this value of Y1. Then if I increase X from X1 to X2, if I increase X from X1 to X2, then what happens to the value of Y? The value of Y comes here. So this is your Y2. This one goes down. Okay. So this is a negative. This is a positive. So positive and negative will give you negative. Or you can look at it from the other perspective. You say, if I decrease X, so if that is negative, so what is happening to the value of Y? You notice that, so this was the value of Y. So you find that the value of Y will be increasing from Y2 to Y1 in this case. This is positive. So this positive and negative, which gives us negative. And then here we also have positive and a negative. Okay, so that's what this is, positive correlation. Maybe I should have labeled it. This is positive correlation, and this is negative correlation. Basically, that's what we call correlation, and that's how you measure it. Huh? So now let's look at the various ways of studying correlation. Methods. Studying correlation. Nicholas.
Oh, sorry. So yeah, if you draw a Cartesian plane like this one, and then you end up with a parallel line, which is a line which is parallel to the x-axis.
Yes.
How do you call that? Is it negative? Is it positive correlation?
We can just look at it. Huh?
Okay.
I want us to follow the same argument. Huh?
Okay.
We can have a third one here. We can have a third one here. And this is our y, this is our x-axis. Then we are having a line which looks like that. It can also be vertical. Right? So let's see what happens. I pick a point here. I have another point here. So this is x1, and this is your y1. Okay. So that's the point x1, y1. Then I have another point here. So if I increase x to this point, x2. Okay, so what happens to y, to y2? It is the same. Can you see that? If I increase x or if I decrease x, then there is no change in the y, in the other variable. So that means there is no correlation.
No correlation.
Yes.
Okay.
There is no correlation, or there is zero correlation. If you change one, the other one is not changing. So it means there's no correlation. You can also have the same argument when the line is vertical. When the line is vertical. So that is it. So let's look at the So let's look at the various ways of studying correlation. And these methods are listed in your notes, so I'll be I'll tend to be a little bit briefer. So the first one is graphically. You can study correlation graphically using what you call a scatter plot. Using a scatter plot or scatter diagram. Okay. Or you can study correlation algebraically. When we talk about algebraically here, means that we're going to use a formula. So there's a problem here. So this means using a mathematical formula. Okay. And there are various ways of, or there are various formula or methods that, algebraic methods that can be used. In this class, we shall focus on two of them, Pearson's correlation coefficient, and number two, we have Spearman's rank correlation coefficient. There are other methods, but we are only going to, there's another method, another main method, but you're only going to focus on these two. Okay, so let's briefly look at the graphical method of studying correlation. You notice that the graphical method is a very subjective way. It gives a very subjective answer to the question of correlation. But usually it's always a good starting point when you're analyzing data. You start by, you plot them, then you have some idea about the kind of relationship we have. If there's evidence or there seems to be some evidence of relationship, then you can go ahead and use the formula. So usually we start graphically before we go to the formula method, because when you use a graph, it's kind of appealing even to people who are not quantitative or who are not into mathematics so much or statistics. So using a scatter plot, using scatter plots. So there are several scenarios. There are several scenarios that can be observed when you use a scatter plot to study correlation. The first scenario, you can plot the points. This is your X variable, this is your Y variable. You can plot the points, then they happen to fall on a straight line, all of them. All the points fall on a straight line. That can happen. So if that happens, you say that the two variables, X and Y, are perfectly correlated if the points are falling on a straight line. Then if the slope, or if you fit a trend line there and the slope is positive, you say there is perfect positive correlation. Like in this case, the slope of this line here, of this straight line here, is positive. So here we say there is perfect positive correlation. That's a very rare scenario, especially when you are using data collected from the field, like economic data and so on and so forth. That's a very rare scenario, okay? Number two, the second possible scenario. So this is what corresponds to a correlation coefficient of +1, the perfect positive correlation. The number two, you can obtain a scatter plot that looks like this. This is Y and X. Remember, I can switch X and Y. It doesn't matter what I put on the vertical axis, but for convenience, I'm putting Y on the vertical axis, but I don't have to put it there for correlation. For correlation, I can switch the variables and put, I can switch their positions. So a more realistic case, you can plot the points. You find that they are not forming a straight line, but they are forming a narrow band, very narrow band of points like that. Very narrow band of points. So in this case, we say there is high positive because of the direction correlation. There is high positive correlation. a third possible scenario. Of X and Y. You can have the points are a little bit dispersed. There is evidence of positive trend, but the points are a little bit dispersed. So they form something like a wider band. It's a wider band of points, huh? But there's evidence of positive slope. So this one, you can call it either moderate or low positive correlation. So that's where the subjectivity comes in. Huh? Somebody may want to call it low, somebody may want to call it moderate. Huh? Okay, so there's some freedom of how you express it. All right, so this is number 3. The number 4, you can plot the points, and again, you end up with a straight line, but now which is sloping in the negative direction. So you can have something like that. So this is again perfect negative correlation. Then we can extend it to this scenario. You can have a narrow band of points, evidence of negative slope. Huh? So this is high negative correlation. High negative correlation. You still can have this scenario. The points are more dispersed now, but there is evidence of negative slope. Huh? The points are dispersed, there is evidence of negative slope. So this is, you can call it low negative correlation. Then there is what my friend was asking there. This is number 5, number 6, number 7. You can plot the points and there is no evidence of positive or negative trend. Most of the cases you find that the points are forming a circular band of points. The points seem to form a circular band of points like that. Okay. So in such a case, so this is Y and this is X, you say there is no or there is zero correlation. So the two variables are not correlated at all. Again, these are very rare scenario, but if you happen to get it, you don't even need to go to the algebraic method. You may want to stop there. You may want to stop there. When you are dealing with the situations, especially situation number 2, 3, 4, and 5, those situations may suggest that you may want to find what we call the cause and effect. And cause and effect is not given by correlation. Cause and effect relationship is only obtained through regression analysis. So if you're observing scenario 2, 3, 4, and 5, you may want to go ahead and perform a regression analysis to check which variable seems to depend on which one. Then you are able to now predict or to do forecasting, forecasting the dependent variable given the values of the independent variable. But when you have number 7, you don't proceed to regression. You just stop there and perform maybe other analysis, but not beyond there. All right, so that's the algebraic way of studying correlation. So that's how you can plot the scatter plots. Then you comment about the relationship, either the strength, like here the word higher is giving us the strength, and this is the direction of the relationship. Okay. Now let's look at the algebraic methods. Algebraic methods. And we shall start with what we call the Karl-Pearson's. Karl-Pearson's correlation coefficient. We say that this is usually denoted by small letter r, defined by this. we say that R is equal to COV X and Y divided by S of D of X multiplied by, that dot here means multiplied by SD of Y. Okay. So where COV XY is the covariance of X and Y defined by, we say covariance of X and Y is given by a summation of this product of deviations. We find the mean. It is some mean, the mean of this product of deviations. Okay, so X minus X bar multiplied by Y minus Y bar. You sum up, then you divide by N. Then SD of X is the standard deviation of variable X. Then SD of Y is the standard deviation of variable Y. So how do we get the standard deviation of a given variable? Square root summation X minus X bar squared divided by N. Assuming the sample is, the size is larger. Then here, summation of Y minus Y bar squared over N. So I can now plug in these three items. I can plug in these three items into this formula and get a better version of the same. So I'm going to have R is equal to summation of X minus X bar minus Y bar. If I bring these three guys up there, then I try to simplify a bit, I'll end up with this formula. This should be easy to see, yeah? X bar squared multiplied by summation of Y minus Y bar squared. You notice that the ends will cancel. So this N will cancel with these two, because these two are square root of N times square root of N, which gives us N. So these two will cancel this one. And you'll be left with a square root of summation of X minus X bar squared and a square root of summation of Y minus Y bar squared. So you end up with this formula, which can be simplified into another version. I think that version is what we'll see in most of the textbooks. But for me, I prefer to use it the way it is. So if you know the other formula, please continue using it, still okay. So X minus X bar, like that. Okay, so we note that R is a number between +1 and -1. R is a number between -1 and +1. That's true for all the correlation coefficients. So let's have an example. Let's pick the example from the notes. Let's pick the example from the notes. So let's pick this one. Which one? So let's work with this data. So let me transfer this information to the other side. So we have we have x 64, 6. Then we have y is 66, 7, 65, 68, 70, 68, and 72. Okay, so let's find the Carl Pearson's correlation coefficient for this data. Of course, we need x bar and we need y bar. So we can compute that separately. X bar is 67, this is 68. So I need deviations from, so I need x minus x bar. So 64 minus 67, this gives me minus 3, minus 2, 0, 1, plus 2, and plus 3. And I also need y minus y bar. So this will be how much? Minus 2, minus 1, minus 3, 0, plus 2, then minus 2. No, this is 0. This is 0. And then this is 4. So we have those. We rarely ever use those two columns the way they are. So we only use them to find out some other more meaningful values. So we need x minus x bar multiplied by y minus y bar. So this will be a 6, a 2, a 3, a 0, a 2, a 2, a 12. So I need this summation here. So summation of x minus x bar, y minus y bar. You need this, that summation. Then the denominators will be coming from the square. So x minus x bar squared, y minus y bar squared. So these values will be 9.
The second last value, 2 times 0 is 0, not 2.
Oh, sorry, yeah. Thank you. This is 0. Thanks for that correction. So this is 0. So let's square these values. So this is 4, 1, 0, 1, 4, and 9. 1, 9, 0, 4, 0, and 16. So this is a summation of x minus x bar squared, summation of y minus y bar squared. So let's get those totals. So the first value, what's the first summation value?
25.
5.
28.
28.
28.
28.
34.
And 34. Okay, so now from there we can obtain R. We can say that R will be equal to divided by times. This will be a positive answer, so you'll report it as a positive value.
Zero point 8102.
8102.
8102.
Yeah, we can keep it there. 0.81. So here we say that, so the interpretation, so there is a high because the number is 0.8. So you use the chart, you can use the chart here. Remember we said that any value above 0.7, you can claim it is high. Okay, so this is a value which is somewhere here. This is 0.7, so that's a value which is somewhere here. So there is a high positive correlation between X and Y. High positive between X and Y. Between X and Y. Okay. So you'll notice that in some of the textbooks, so basically that should be it about correlation. So alternative formula, which is just the above formula. After you play around with the values, you notice the formula is R. Some of you remember this formula offered. R is equal to N summation of X times Y. If you don't want to get the X bar values, you can use this formula and you'll get the same answer. Divided by the square root of what? Should be the square root of N into summation of X squared minus, let me check something here. So minus summation of X squared, summation of X, and there's a bracket like that. Then here you have that kind of brackets. Then here you have summation of Y squared minus summation of Y. So you can use that formula also. It's equivalent to what we used earlier. The same. Okay, so you can repeat the above example using this one. So now you don't need to find X bar and you don't need to use X bar and Y bar. All right. So basically that is it. Now let's look at the Spearman's rank. Spearman's rank. Correlation coefficients. Spearman's rank correlation coefficient. So this one is usually denoted by, just to differentiate, usually denoted by rho. We use the Greek symbol. We use the Greek symbol rho. Rho is just the letter R, but not from the Greek. And defined by, so we use this formula. So rho is equal to 1 minus 6 sigma d squared. Please mute your microphone if the noise is coming from your side. D squared then. This is a D, yeah? So where D is the difference, let me call it D squared, is the square of the difference. The D squared is square of the difference between two corresponding ranks. Between two corresponding ranks. Two corresponding ranks. Okay, so of course we are summing that. Then N is the number of observations. Is the number of observations being ranked. The number of observations being ranked. You can think of a situation where you sit for an exam, then that exam is marked by two independent lecturers, and each one of them awards you marks independently. So somebody may want to check whether the marking was fair. And usually that's what happens in universities, because once your exams are marked by your lecturers, usually the external examiner comes and checks through. Of course, they do a random sample. So they check through and check whether the marks that they are awarding and the marks that were awarded by the unit lecturer are consistent. So we expect to find a high positive correlation if the two markers are consistent or if they are fair, okay? So if we find that, then usually you compare the ranks. If I have a class of 20 and all of them are marked by two people, you rank the students according to lecturer 1, and you also rank them according to lecturer 2. Then you compare the ranks and check whether the ranks are consistent or not. So basically that's what we call the Spearman's rank. So for lack of a good data set, let's work with the above data set. So let's work with the above data set and find the Spearman's rank coefficient of correlation. So let's recall that data set. We had 64, sorry, this is X and Y. It was going from 64 to 65, 6. Those are the values. And then the values on the Y-axis were 6, 67, 65, 68, 70, 68 again, and 72. Okay, this is just for illustration purposes. So let's find the Spearman's rank correlation coefficient for this data. So the starting point, assume now these are 3, 4, 5, 6, 7. These are 7 students, and they have done some exam. And then the exams are marked by lecturer A and lecturer X and lecturer Y. and they have awarded the marks are shown there. You may want to check whether there is consistency or maybe a high correlation in the way that exam is being marked. So here you start by ranking the values according to each of the variables. So let's rank X. We rank the X's. I prefer to rank from, having the highest value getting rank number 1 or position number 1. So for X variable, this would be my number 1, number 2. So if you rank the other way around, there's no problem. If I rank them the other way around, there will be no problem. But I have to rank the same way. So I also come here, rank Y. So I want to rank the marks of Y. So number 1 here is the guy with 72, followed by the guy with 70. So that's my rank number 2. Then I have a tie here. There are 2 guys who have 68. So they have tied. So you break the tie. So you can assume in the background, assume this is your number 3 and this is your number 4. You need to find the mean of these 2 numbers. If there was another 68 here, I would assume this is 3, 4, and 5. Then I would find the mean of 3, 4, and 5. So in this case, I'm finding the mean of 3 and 4. So I just take 3 plus 4 over 2, which is 3.5. So the rank of these 2 people here will be 3.5 here and 3.5. Then, yeah, and then my next rank will be rank number 5 because I've already utilized the 3rd and 4th position. So the next guy will be number 5, and that is 67. So this will be number 5. Then this will be number 6. Is it so? Then this will be number 7. So those are the ranks according to Y. So basically we analyze this information now. We analyze that information. We analyze that kind of information. So we need to get the difference between corresponding ranks, but I need to have it squared.
The condition is critical. We don't allow any visitors in the intensive care unit.
Johnson Mwatu, you are watching Maria. Okay, so let's get D squared. The difference between pairs of corresponding ranks. So this would be 7 minus 6, which is 1 squared, will also be 1. This will also be 1. This will be 4. Okay, this will be how much?
0.1.
Excuse me.
Yes.
At rank number rank X number 70.
Yes.
I think it's number 2.
For X.
Yeah.
We have a value higher than 70 in the column of X. Is the highest. Is our rank number 1. Huh?
X should be 2. 70 should be 2, not 3.
70 should be. Which are we talking about? Which one are we talking about?
Rank X.
X, huh? What is the highest value in the column for X?
72.
70.
So I think it's okay.
I think it's correct. You're talking about Y.
This is the correct value, isn't it?
Talking.
Yes.
Correct.
It's okay, isn't it?
Yeah.
And this is 0.25. Then the next one should be 1.
0.25. 1. 2.25.
Yes. The next one, huh?
0.25, yes.
2.25.
2.25, correct. 2.25. And then this will be 0. So this is now what we are calling summation of B squared. Summation of B squared. gives us
10.5.
9 or 10.5.
9.
9.5.
9.5.
Okay. Then
9.5.
of course we know the number of observations here is 7. So our row will be 1 minus 6 times 9.5 divided by 7 cubed minus 7. You either report a positive answer or a negative answer or a 0.
.0.83.
Yeah, we can keep it then. So again, this is a high positive correlation. So if these are marks of students, maybe some 7 students, and 2 independent lecturers mark them, then you can say there is a high positive correlation in the way the exams were marked. So there seems to be, it seems to have been marked fairly. Seems to have been. But if you find a negative, for instance, it means that whoever was my student number 1 is possibly your student number last. So it means that there's a serious problem with the way maybe the marks were awarded and so on and so forth. So that is it about correlation analysis. I want us to switch to regression analysis if there's no question. And as you'll notice from the notes that we have different types of regression analysis. We have simple regression analysis. We have multiple regression analysis. We have linear regression analysis, non-linear regression analysis, partial regression analysis, and even total regression analysis. But our focus here will be simple linear regression analysis as well as multiple linear regression analysis. So we'll be talking about simple linear regression analysis. So when we talk about regression, we talk about now, remember in the correlation, we are talking about the degree and direction of relationship between 2 variables. When we talk about regression, we talk about the average relationship, the mean relationship between 2 or more variables, And the main objective of regression analysis is the prediction or forecasting, use that word, of the dependent variable when given the values of the independent variable, when given the values of the independent variable. I know many times we use y for the dependent variable and x for the independent variable. That doesn't have to be the case. You just need to know which one is your dependent variable, which one is your independent variable. When we talk about linear, the word linear here tells us the kind of relationship we have between the variables. So it means that it's a straight line kind of relationship. So the relationship can be represented using a straight line kind of in quotes, relationship. The relationship can be represented using a straight line okay, is a proportionate kind of relationship. That's a proportionate kind of relationship. Then when we talk about simple here, simple means with two variables only, where one is the dependent variable, and the other is the independent variable. Okay? So maybe I can also mention this so that I can avoid it later. When we talk about multiple, it means that we have more than two variables. So in this case, that's a bivariate case. So in this case, we talk about a multivariate case. More than two variables, where one is the dependent variable and two or more are independent variables. That's what we should be calling multiple regression. So we shall be talking about simple linear regression and multiple linear regression. Now let's look at a simple expression here. So let's say that the simple linear regression equation of variable y on x is given by, so the simple linear regression equation of variable x on y is given by this kind of equation. It's a straight line equation. Y is equal to, we use beta naught plus beta 1 of x. I know you're used to these, huh? Y is equal to a plus b of x, the same thing. But in regression analysis, we prefer to change these constants into the betas, beta. We call them beta. These are Greek symbols. So the simple linear regression equation of y on x is given by that. And you should also be able to notice that the regression equation of x on y, if I were to reverse the order, then the equation also changes. So you're going to have x is equal to, say, beta naught plus beta 1 of y. So it's always very good for you to notice what you are regressing on what. Regression of y on x. It is different from x on y. So back to regression of y on x. Back to the regression of, so let's consider this regression equation, 1 of x. So y here is called the dependent variable. Y is the dependent variable. And then x is the independent variable. Then beta naught and beta 1 are the regression coefficients. Sometimes we call them parameters. And once you call them parameters, you know that parameters are always unknown. Okay? And they are always unknown. They are always unknown. They are always unknown. So if they are unknown, it means that at some point we may want to estimate them. And that will be one of the, that is one of the main tasks when you are regressing, estimating the values of beta naught and beta 1. Various methods, and we shall discuss one of them. So beta naught is, you can call it the y-intercept, or value of y when x is equal to 0. The value of y when x is equal to 0. Then beta 1 is then beta 1 is the slope. I'll give more details later. The slope coefficient. The slope coefficient. So this tells us the gradient of the line. The gradient of the regression equation of the line itself. We'll be looking at it in details later. So when you are performing regression analysis, the natural starting point is a scatter plot. Just like we saw in the case of correlation analysis, a good starting point will always be a scatter plot. And for regression, you cannot switch the position of y and x. So the dependent variable is always on the vertical axis. Dependent variable, this is your y. The independent variable will be in the x-axis. Independent variable. So here will be x. So suppose you draw a scatter plot and you observe that. We talk about a regression equation, we're talking about a line, a mean line, a line that best represents these points. Okay, there are so many ways of doing that. You can fit it anywhere. Okay, so let's assume that it is here. Assume that this is the line we're talking about. So this is the point we are calling beta naught. That point here. And you see, you cannot know that point in advance. From the data, by just looking, you cannot just know it. You have to compute it. You have to estimate it. Then the slope of this line, and we know the slope is given by change in the vertical axis divided by change in x. So the slope, that is beta 1, is given by that. Okay, that value again, you cannot just estimate it. It is not easy to estimate it by just observing the data. Okay, so there are various ways, because already we have said that these parameters are always unknown. There are various ways of estimating these values. There are various ways of estimating these values. And one of the most widely used method of estimating the values of beta naught and beta 1 is what you call the ordinary least squares method. It's also called OLS. Huh? We'll be discussing this thing again when you go to econometrics. So for those in finance, you're likely to do this in detail. Huh? So this is also called the OLS, the ordinary least squares method. And the theory behind OLS is quite simple. So it states that once you have the scatter plot like this, then you need to fix a line. You need to fix a line within those points in such a way that if you measure these distances, you measure for all of them, the distance between the line that you fitted, you measure those distances like that. Let's say this is D1, D2, D3, the order is not important, D4, D5, there's also a D6 here, D7, and D8. You get those distances, then you square all of them. You get the distances, then you square them. So that means you take, and then you sum. Huh? So you're going to have D1 squared plus distance 2 squared plus all the way to the last one. If you sum this, you should get, it should minimize that sum of square of those distances. A line that minimizes this function here. A line that minimizes the sum of square of these distances is what we are calling the regression line. And usually we prefer to call it the line of best fit. Because you notice there are infinitely many possible lines that you can fit for any given data set. But there is only one line that will minimize these squared deviations. There's only one line. That line is the one that we're going to call the line of best fit or the regression line. So basically that is it. So, so we're saying that the theory here is, so here we attempt to draw a line which minimizes the sum of square of the distances. These are vertical distances. So here we attempt to draw a line which minimizes the sum of square of the vertical distances from the individual points the fitted line. So we attempt to draw a line which minimizes the sum of square of the vertical distances from the individual points to the fitted line. So such a line, the line obtained using this approach is called the line of best fit. Yeah, and this is the regression equation that we are looking for. Okay. So when we talk about minimizing the squared distances or the squared deviations, that tells you that at some point we may want to apply some calculus, especially differentiation, because minimum points of functions, because of course these observations here or these values here are likely to come from a quadratic function. As you can see, we are squaring something. So we're likely to come up with a quadratic function. We are likely to have a quadratic function. And we're looking for this point, the minimum point. So this is a minimum of the sum of deviations. So this point here can be obtained using differentiation. But you're going to avoid that route of differentiation. We're going to skip that bit actually. And then we go to a friendlier way of obtaining these values of beta naught and beta 1 using the same approach. Okay. So to estimate the values of beta naught, the values of beta naught and beta 1 using the OLS method, we solve the following two normal equations. In the case of simple linear regression, in the case of simple linear regression. So we have simple linear, that means we have only two variables, x and y. So we solve some equations, which are very simple equations called the normal equations. They are linear equations, which we solve simultaneously. So if we have three variables, like in the case of multiple linear regression, you're going to have three normal equations. So if you have 10 variables, you shall have 10 normal equations, and so on and so forth. But for the purpose of this class, we shall be giving illustrations up to three variables, So using the regression equation, y is equal to beta naught plus beta 1 of x. If we use that equation, we want to estimate the values of beta naught and beta 1. So I'm supposing that in the background, you have some data containing the variables x and y. And we know the variable x has observations x1, x2, all the way to xn. Y the same way has y1, y2, all the way to yn. So that's the data you have. You want to estimate the values of beta naught and beta 1. So the first normal equations, is, so the normal equations for this type of equation are, number one, you take this equation here, you sum each term. So these are the terms. This is one term, another term here, another term here. You sum each term n times. N is the length of the data set. Huh? So you take this plus that, plus that, plus that, plus that. So you end up with summation of y. Okay, then these are constant here. These are constant. So you have beta naught, all the way to beta naught. You have n of them. You have n of them. So you take beta naught plus beta naught plus beta naught plus beta naught all the way. You do that n times. So what do you get? If you sum beta naught n times, what do you get? We have beta naught plus beta naught plus beta naught plus all the way to plus beta naught. This is 1, 2, 3, all the way to n. There are n of them. So what do you get if you add up beta naught this number of times? What do you get?
N beta n.
You get n beta naught. N beta naught. You don't get summation of beta naught. You get n beta naught. And then of course you also sum this. So the first normal equation is given by summation of y is equal to n beta naught plus beta 1 summation of x. That's the first normal equation. You notice that these are values you get from the data. Summation of y, you just need to come here and sum the data. The same case with x. And then n is the number of observations in the data. So these are straight line equation with two unknowns, beta naught and beta 1. Now the second normal equation, you go back to the regression equation. Take your independent variable, which is x. Take your independent variable. Multiply every term by the independent variable. So you end up with xy is equal to beta naught x plus beta 1 x squared. So you multiply everywhere by the independent variable. Then you sum. You sum every term. So you're going to have summation of xy is equal to beta naught summation of x plus beta 1 summation of x squared. So that's what you have. So these are the normal equations which we need to solve in order to find the values or estimates of beta naught and beta 1. So if you have three variables, you use the same analogy, and you're going to see if you have, maybe you're going to see that in the next example. So let's have an example, a simple linear regression case. Example. So let's get the data from the notes. Huh? Moneki, is there a problem? Oh, this was a long time ago. Eh?
No problem.
There's no problem, all right. So Faisal, Mohammed, your hand is up.
Yes, Malim.
Yes. You have a question?
Yes.
Yes.
It's about the Spearman's rank correlation.
Yes.
The example you had given.
Yes.
Where you grouped the ranking, the values. I didn't understand where you got those 7, 6, 5, 4, 3, 2, 1.
Oh, maybe we need to go back there. Spearman's rank. That was some time back. Which values?
When you had grouped the values of the rank X and the rank Y. I understood the D squared, but I didn't understand the values.
Oh, the values, huh?
Yeah,
Like which value?
like in the category of rank X, where you got the 7, the 6, the 5, the 4, 3, 2, 1.
Oh, the ranks, huh?
Yeah.
You feel, can you imagine a situation where I give you a test and then I rank you from student number 1 to student number last? Huh?
Okay.
That's what I've done. So if you
I
assume these
understood.
are marks of students, huh? So the student with 70, I give him rank number 1. The one with 69, I give him rank number 2, and so on and so forth. But I can also reverse the order and say, the guy with 64 is my rank number 1, and so on and so forth. Okay, you got it, huh?
Okay. Yeah, I understood. Thank you.
All right, so let's move on. Huh? Let's have a simple example. We have some data here. I want to make it visible. We have some data here, X and Y. So the values of X are 6, 2, 10, and what? 1, 8. Huh? Then here we have 9, 11, and 7. So assume the objective is to regress Y on X. Regress Y on X. That example is in your notes, so you can find the other story in your notes. Huh? So when you're told to regress Y on X, it means that we need an equation of the form. We need an equation of the form Y is equal to beta naught plus beta 1 of X. So you want to predict Y given values of X. The normal equations corresponding to this, normal equations corresponding to this regression equation here will be the first one, summation of Y is equal to N beta naught plus beta 1 summation of X. And the second normal equation will be summation of XY is equal to beta naught summation of X plus beta 1 summation of X squared. So I need to get these values of summations from my data. So it's good practice to have your table looking like this. So we have 6, 2, 1, 8. This is 9, 11, 5, 8, and 7. So I want to complete the first normal equation. And the first value I need is summation of Y. So you'll come to your data and sum Y. So summation of Y. You come to your data and sum Y. So this will be how much?
40.
40, thank you. Then I need N, number of observations, 1, 2, 3, 4, 5. I need summation of X. So you come here and say summation of X.
30.
30, thank you. So the first normal equation will look like this. 40 is equal to 5 beta naught plus 30 X. 30 what? 30 beta 1. So that's the first normal equation. It is a straight line with two unknowns, beta naught and beta 1. And those are the guys we are looking for. Now let's go to the second normal equation. We need X times Y. So X times Y. You can get these values. Huh? So this is what? 5, 4, 2, 5, 0, 3, 2, 5, 6. Huh? We need summation of XY.
214.
214, correct. Thank you. Then I have summation of x. I need x squared, so I need to square x. Huh? This is 36. This is 4. This is 16.
$220.
0. Right, so the second normal equation will look like this. Huh? This will be 240 is equal to summation of x, which is 30, plus 220. So I have a pair of linear equations. Okay, so I solve them simultaneously using any method of my choice. Huh? So we solve these. We solve these simultaneously. So you can use elimination method, substitution method, and other methods. So let's choose elimination method. Let's eliminate beta naught. Let's eliminate beta naught. So I'll multiply the first equation by 6. Huh? Yes. So this gives me 240. 180. I keep the second equation the way it is. Huh? So this is 240 minus 14. And this will go away. This is minus 40.
40.
Minus 40 beta 1. So from there, we can make beta 1 the subject of the formula.
26 plus 12.
Minus 0.65. Remember, the value of beta 1 and beta naught are always unknown. They are always unknown. So what we have is an estimate of beta naught, of beta 1 using the OLS method. So to show that it's an estimate, you put a hat here. You put a hat on top there. So this is the estimate. So this is the estimate of beta 1. Beta 1 is always the parameter. So we have the sample statistic. Now, using this value, we can also get the estimate of beta naught. We can use the first equation. Or using the first equation, using the first normal equation, we can get that what is this is 40 is equal to 5 beta naught 30 minus 65. So we get that beta naught 11.9. And again, this value is not the true value of beta naught. It's an estimate. So you put a hat like that. It's an estimate. So this is the estimate of according to this method. Okay. So now with those two, you can write now your regression equation. So the required regression equation The required regression equation is y is equal to beta naught 11.9 plus beta 1, which is minus 0.65 x. But because beta naught and beta 1 are estimates, even the value of y will be an estimate also. So you put a hat there. You also put a hat there. So that is an estimate of y. So this one shows an estimate. So this is not the true value of y. You'll get an estimate of y. An estimate of y. Okay, so this is the equation that you can use to make predictions. So if you are given any values of x, you can make predictions. You can make even forecasting. So for instance, in the data, we were given some values of x. You may want to estimate the value of y when x is, let's say, 12. When x is 12, you can predict the value of y using that equation. So what this equation means is that if you were to plot, if you were to sketch it, would have something like this. As you can see, the slope is negative. So, and then it's cutting the vertical axis, then it's a negative slope. So it would have something like this. Would have something like that. So this is y estimate is equal to 11.9 minus 0.5 of x. Is sloping negatively like that. So this is your y, this is your x. So with this one, you can make predictions. You can predict this way and also this way. You can extrapolate like that. So now, how do we interpret these regression coefficients? Interpretation. Well, we start with beta naught, which is 11.9. So we say that this means that the estimated value of y when x is 0 is 11.9 units. So the estimated value is an estimator. The estimated value of y when x is 0 is 11.9 units. So if you put this guy as 0 here, then this is what remains. That's what it means. That is straightforward. In most of the cases, especially in economics and business, that value may not be very meaningful. May not. You can think of a situation like that, one of demand and supply, and you're talking about a situation where the quantity supplied is 0. Then you want to talk about the price. It would not make sense for you to say that this is the quantity supplied when the price is 0. It will not make sense. Okay. Then the slope coefficient is actually much more interesting. Beta 1 estimate, which is minus 0.65. So this means that for every unit increase in the value of x, for every unit here means 1, increase. Unit increase means plus 1. If you do plus 1 on the x, then what happens to the y? That's what you're calling beta 1. So for every unit increase in the value of x, the estimated value of y, decreases because of this negative sign here. So this negative sign here tells you the relationship is inverse. So as you increase x, then y will be decreasing because of the negative sign, decreases by 0.65 units. So if that value was plus 0.65, I would say the estimated value of y increases by increases. So whether I say decrease or increase depends on that is there. So that's how we interpret the slope coefficient. That should be easy to see, yeah? That should not be very difficult. That should not be very difficult. And that should be it about simple linear. We have very few minutes remaining, but I want to mention multiple linear regression. Briefly, let's look at multiple linear regression, which is just a simple extension of what we've just mentioned. So multiple, yes. Yes, yes.
We are pumping too much today.
All right, so what are you suggesting? So I'm saying that we are, I know the time is up, but I'm asking that we just sacrifice a few minutes, we finish. Yeah? So please, if you don't mind. All right, so let's look at multiple linear regression, and let's consider the regression, the linear regression equation of, let's say, y on x and z. When you see that, that means that this is your dependent variable. This is your dependent variable. And these two are your independent variables. Okay. So in that case, the regression equation will be of the form, y is equal to beta naught plus beta 1 of x plus beta 2 of z. So that's the regression equation of y on x and z. So if I said regression equation of z on x and y, I'll be talking about z is equal to beta naught plus beta 1 of x plus beta 2 of y, and so on and so forth. So it's always good for you to note what is being regressed on what all the time. So the normal equations corresponding to this equation are as follows. So the normal equations, because we have 3 variables, we shall be having 3 normal equations. If you have 2 variables, you have 2 normal equations. If you have 10 variables, you know you have 10 normal equations. So the first normal equation, you sum each term here n times. I'm assuming my sample size is n. So this will be summation of y is equal to n beta naught plus beta 1 summation of x plus beta 2 summation of z. That's the first normal equation. Please notice that we are multiplying beta naught by n. The second normal equation, I will take my first independent variable, x in that case, I multiply everywhere by x, then I sum. So I'll end up with summation of xy is equal to beta naught summation of x plus beta 1 summation of x squared plus beta 2 summation of xz. The final normal equation, I take my other independent variable, which is z, multiply everywhere by z, then you sum. So I'll end up with summation of yz is equal to beta naught summation of z plus beta 1 summation of xz plus beta 2 summation of z squared. So those are the normal equations I need to solve simultaneously. Those are the normal equations I need to solve simultaneously. So here, I'll be having linear equations with 3 unknowns. So I just use the same method, but it will take a little bit longer for you to solve that. So let me give a small example with a small n. So example, I want to check x, let's take 1, 2, 4, 5, then y we can talk about I hope the numbers will not be problematic. Huh? Then Z, and guess some values of Z. I'm hoping this data will behave very well. All right, so suppose I want to regress. I want to regress X on Y and Z. Huh? I've changed. Huh? In the example up above, I was saying regress Y on. So now I want to regress X on the other variables. Okay, I think there's a question. So, so in this case, if you are regressing X on Y and Z, the required regression equation is of this format: X is equal to beta naught plus beta 1 of Y plus beta 2 of Z. That's the equation that we are trying to fit. The normal equations from there, we have 1 summation of X is equal to N beta naught plus beta 1 summation of Y plus beta 2 summation of Z. Second normal equation, I take my first independent variable, I multiply throughout, then I sum. So this would be summation of XY is equal to beta naught summation of Y plus beta 1 summation of Y squared plus beta 2 summation of YZ. And finally, I take Z, multiply everywhere, I end up with summation of XZ is equal to beta naught summation of Z plus beta 1 summation of YZ. And finally, we have beta 2 summation of Z squared. So once you get the normal equations correctly, the remaining part becomes quite easy. Because I just need a few summations here and there. So maybe you can quickly do this. The first normal equation, I need summation of X. So I need summation of X. This will be how much? 15, huh? Is it 15? That's 15, huh? Then N is 5. Summation of Y is 25, huh? You are saying? 20?
3.
20 what? 23?
3.
23, thank you. Then I need summation of Z. Huh?
26.
So let me have the first normal equation. So this will be 15 is equal to 5 beta plus 23 beta 1 plus 6 beta 2. That's the first equation. The second one, I need X times Y. So I need to multiply X and Y, then I sum. I need X and Y summation. I need the summation of X, Y. XY will give us how much? This is 3 plus 76.
76.
76. I already have summation of Y. I need Y squared. I need Y squared
William, I can't see where you're writing.
Why?
I don't know. I can only see the three questions.
You can't see the screen.
I can see the screen of the part where you've written the equations. I can't see where you're writing right now.
So anybody else who has the same problem? Or you may need to minimize, you may need to minimize the list of participants. So I need y squared. So this would be, yeah,
139.
39.
139. Huh? There are people who cannot see.
Can't see where you're writing.
So what is blocking? Is there anyone who can see everything that I'm writing?
We're writing some things.
We can see now.
We can see.
Yeah, we can see.
139.
Yes.
Then I need y times z. I need yz.
15, 63. Oh. 6, 48.
$129.
138.
38.
Thank you.
38.
So our second equation will be xy. We have 76. Summation of y, which is 23. Not plus y squared 139. Beta naught. Sorry, beta 1. Huh? And yz, which is 138. Oh, they're very close. Huh? Beta 2. Now the last equation, xz. Huh? We need xz. This is So we have summation of z. Summation of z is there. We have yz. We need z squared. Z squared is 25.
$62.
162. 162. So let's write the equation here. So this is xz, which is 73, is equal to summation of z, which is summation of z is how much? 26, huh?
Yeah.
We have summation of yz, 130. And finally, we have 162. So these are linear equations. So you solve them simultaneously. You solve them simultaneously to obtain the values of beta naught, beta 1, and beta 2. Because this will take us some time, I want to share with you the final answers. Then we interpret, then you try to get them at home. Hope that will be okay. So I want to do them somewhere. I want to do this guy somewhere here. So I want to define my variable x. Variable x has the values 1, 2, 3, 4, and 5. My variable y has the 3, 7, 1, 4, and 8. Hope that is correct. 3, 7, 1, 4, and 8. And then my variable z has the values 5, 9, 4, 2, and 6. Then I can do this. Say press X1, Y, and Z. That should be it. So, so the value of beta naught will be 3.4478. So beta naught will be 3.4478. And the value of beta 1 estimate will be 0.5073. And finally, the value of beta 1, beta 2 estimate will be minus 348. So confirm these values at home. That we go to the interpretation of the regression coefficients. So beta naught estimate 3.4478. This is the estimated value. What are we predicting? The estimated value of x when both y and z are 0. When you put both y and z to be equal to 0, then the estimated value of x will be equal to that. Okay. The one and the two are more interesting and more meaningful or more useful in analysis. So beta 1 estimate, which is 0.5073. This is how you interpret it. You say holding the other factors constant, the other factors or variables. So here you interpret in that manner. You hold the effect of the other variables constant. We say that, so holding the other factors constant, we say the estimated value of x, the estimated value of x, that's our dependent variable, increases by 0.5073 units for every unit increase. For every unit increase, the value of y. So this part is important. You must assume, you must control the effect of the other variables. Then now you interpret. So this is like partial kind of interpretation. So the value of beta 2 can be interpreted in the same way, minus 0. This means that if you hold, holding the other factors constant, that includes variables. We say the estimated value of x, the dependent variable, decreases by 0.5348 units for every unit increase. For every unit increase in the value of z. So you notice that the interpretation here is slightly different from what we saw in the case of simple linear regression. And that marks the end of that topic. You'll get much more examples in the notes. So please check out and